So in this video, we will see about linear and binary search. So the problem statement is you will be given with one array of size n and a key value. So we got to found whether the key is present in the array or not. So on the linear search, so this is a brute force approach. This is the given pseudo code for that linear search. So this A is a array and n is the size and key is the element to be found. So in a brute force approach, we use a for loop. The for loop starts from the first element to the last element, index of the first element to the last element. Actually, in a conventional program language, the first element index is 0, last element index is n minus 1 for the simplicity. So I use the starting element 1 and the last element n. So for loop executes from I value 1 to n. So in each iteration, the key value is compared with the current index value, and if it is found, then it returns true. That means the element is found. So once if all the entire for loop is executed and the key is not matched with any of the value, then it will return element not found or false. So the time complexity of this algorithm, for example, so here this is not a divide and conquer approach, so we can use line counter method. So we need to for each line we need to execute how many times that line will be executed, and then for each line we need to find the time taken to execute that line. So that is a line code method. So for this line, this is a for loop. So for loop contains three statements. That is initialization statement. So initialization statement will be executed for only one time. So and then next is the comparison statement. The comparison statement will be executed for n minus 1 time. So and then the increment operation is also executed for n minus 1 time. So and then so this conditional statement, so the conditional statement actual time needed for executing this conditional statement is 1. So but how many times this statement will be executed? So at most it will be executed for n times the length of the for loop. So totally, so it will be n. So the return statement, it will be executed if and only if the condition is true. Suppose if the condition is true at any time, if the condition becomes true, means this return statement will be executed for only one time. So this return statement is also executed for only one time. So in total, in the line code method, we need to add the time taken by each and every line in or each and every statement in the algorithm. So in total, it will be 1 plus n minus 1 plus n minus 1 plus n plus 1. So it will be 3n. So in big O notation, we can represent it O of n. So actually the time complexity, there are two important categories. First one is best case. So best case in a linear search, the best case occurs when the element to be searched is found in the first index. So if the element found in the first index, then this for loop will be executed for only one time. And this if condition will also be executed for only one time, and this return statement also executed for only one time, because the first statement, the first element itself matched with the key. So when I equal to 1, the if condition becomes true and it immediately returns the true. So the time complexity is O of 1. So this is the best case. So worst case occurs when the element is not found. So worst case occurs when the element not found. So and otherwise the element found at the last index. So element found or present at the last index. So in both cases, the for loop should be executed for n times. If the size of the array is n, means the for loop should be executed for n times. So the first for loop, the time taken by for the for loop is 1 plus n minus 1 plus n minus 1, and the if condition will be executed for n time, and the true statements will, that means return statements will be executed for one time. So actually this is O of n. So this is about linear. So next one is binary search. So the binary search is a divide and conquer approach, and this binary search algorithm can be applied for the sorted input. So in the real time, it may be applicable for dictionary search, where the words are already sorted based on the alphabets. Otherwise, a library book search, in which the books are sorted based on the title or ISBN or the author. So here, uh, so in the divide and conquer approach, first the actual simple logic of this divide and conquer is first the key value is compared with the middle element. And if the key value is matched with the middle element, then that middle element index will be returned. Suppose the key element is not matched with the mid value, so and then we need to compare whether the mid value is greater than the key value. So if the mid value is greater than the key value, then definitely that if the key present, it will be present to the left side of the mid value. So because this is sorted, so if the key is less than the mid value, then definitely if it is present, then it should present to the left side. So we are going to do the same process for the left of the input. Suppose if the key is not matched with the mid value, and the key value is greater than the mid value. So if it is greater than the mid value, means so definitely if it is present, then it should present at the right side of the key value. So we are now going to do the same process for the right subarray of the given input. So the given array will be divided based on the key value and the mid value. Suppose this is the input for this given input. So the input contains 7 elements. So that means n is 7. So first we need to find the mid value. So how to find the mid value? The simple calculation is start index plus end index by 2. So mid is index, this mid is a mid index. So start index plus end index by 2. So in this example, start index is 0, end index is 6. 0 plus 6 by 2 is 3. So in the case 1, if the mid element is equal to key. Suppose if the key to be searched is 11, so that 11 should be compared with the mid element at the index 3. So in this example, at the mid element at the index is 11. So the key element to be searched is also 11. Both are same. So the key is found, and we need to return the mid index, not that mid value. We need to return the mid index. That means 3. So this is case 1. And case 2, if the mid value is not equal to the key to be searched, and the mid value is greater than key. So in this case, I already told you, if the key is present, it should present in the left subarray or left side of the key. So we need to repeat the same binary search only on the left subarray. That means the elements belongs which are less than the mid element. So here we need to do only one change. We need to change the end index. So end index to mid index minus 1, and then we need to repeat from the case, repeat the same binary search. Suppose if the key value is 10 and the mid value, now the mid value is 3, so 0 plus 6 by 2 3, and we check whether that mid element 11 is equal to 10 not, and 11 is greater than 10. So 11 is greater than 10 means if 10 presents in this input, it should be at the left side of the 11. So in this case we need to search only this portion of the input. So see, this portion start index is 0, end index is 3. So already the start index is 0 only, so end index already that is 6. Now we need to make it to 2. So what is this 2? 3 minus 1. So this, I just change the end index, mid minus 1, that is 2. This is case 2, and then we need to repeat the same binary search. So in the case 3, suppose case 3 is that mid element is not equal to key and the mid element is less than key. So if the mid element is less than key means the key should present. If it present, it should present in the right side of the array. So right side of the array contains the elements which are greater than the mid element. So in this case we need not to change the end index, we need to change the low index. So low index is equal to mid plus 1, and we need to repeat the same binary search for this sub array. So for example, in this case, if the key value to be searched is 12, so 12, and then mid element, now the mid element is 11, so we compare 11 and 18. If the 11 is not equal to 18 and 11 is less than 18, so if 18%, then it should present at the right side of the mid element 11. So in this part, so this is the right subarray. So for the right subarray, the end, this is the end index, end index will not change, so the start index will change. So start index is nothing but what is the current mid index plus 1. So we need to change the start index. So that means low index or start index equal to start mid plus 1. So in this case start index will become 3 plus 1 4, and we need to repeat the same binary search process. So if you repeat this same processes, then when this process this is just a recursive function. So if you recursively call the same function based on the mid value, then at some point of time we need to stop this recursive call. So that is the base condition. So here the base condition is the this recursive call will end if the array contains only one element. So how to find whether the array contains only one element means, if the array contains only one element, then low index as well as end index, start index as well as end index are same. If the so we need to check if low index is equal to high index, or start index is equal to end, then it means the array contains only one element, and by comparing that element with the key we can able to stop this recursive call. Suppose for the given input the key value to be searched is 6. So initially the start index is 0 and end index is 6. So first we need to find the mid index. So mid index is 0 plus 6 by 2, this is 3. So A of mid is now 11. and we compare 11 is greater than 6. So if the 11 is greater than 6 means we need to change end index. So end index equal to 3 minus 1, 2. So now start index is 0, end index is 2. So it contains the left subarray from 2 to 9. So now we need to do the same process for the left subarray 2 to 9. So now the start index is 0, end index is 2. So mid equal to 0 plus 2 by 1. So this is 1. Now we need to compare that mid value a of 1 equal to 6, and our key is also 6. So both are same. Now we need to return the element found at the index 1. Okay. Suppose if the value to be searched is 17. So the key value to be searched is 17. So initially the start value is 0 and end value is 6. So mid will be 3. So mid will be 3 and mid value is 11. So a of 3 is 11. So 11 is not equal to 7. And then 11 is greater than 7. Sorry, it is not a 7, this is 17. So 11 is not equal to 17 and 11 is less than 7. So in this case we need to change the start index. So start index equal to mid index plus 1. So mid index is 3, 3 plus 1 equal to 4. Now we need to repeat the same binary search for this subarray 14, 17, 22. So now we need to repeat the same process for 14, 17, 22. So this index is 4, this index is 6. So now repeat the same binary search, find mid. So mid equal to 4 plus 6 by 2, this is 5. And now a of 5 is equal to 17 and key value is 5, so both are same. So now the key is found and the index of the key is 5. So we need to return key found at index 5. So in this way this binary search will. So now now we will see about the pseudocode of this binary search. So this binary search, this algorithm takes array as a input and then key value to be searched. So low is the start index of this array and high is the end index of the array. So first we need to check base condition. So here the base condition is low equal to high. So it occurs when the array contains only one element. So if this base condition is true, we compare that key with the a of low, the low index, or key with the high index, because both low and high are same. So if it matches, so a of low is equal to key, then we need to return that low index. Suppose the a of low is not equal to key, the key is not same as the single element in that array, then the element is not found, we return the false statement. If this condition false, that means low is not equal to high, this means the array contains more than one element. So in this case the mid value will be calculated. So mid equal to low plus high by 2, and we check if the mid element, the value stored in that mid position, mid index a of mid is equal to key. So if it is true, then we return the mid index value. Suppose if it is not false, mid value is not equal to key, then we check whether the mid value is greater than key. That's case 1. So if mid value is greater than 1 means we need to change the high index value. So high is equal to mid minus 1. So now I call the same binary search with the array, but here the high value is changed. So low, high, and the same key value. We suppose this condition is also false. That means the key value is not equal to the mid value, and key value is not greater than mid value means the key value is less than the mid value. So if the key value is less than the mid value means this is case 3. So we need to change the low index value. So low index value is changed to mid plus 1, and again I call the same binary search with this new low value. So this is the actual pseudocode using the recursive function. The same can be written without this recursive function call. So since this binary search is a dividend conquer approach, it is better to write this pseudocode using dividend conquer approach. Then only it is very easy for you to understand the time complexity of this binary search. So now we will see about the time complexity of this binary search. So first we derive, since this is a dividend conquer approach, we need to derive the recurrence relation for this. So the recurrence relation for any dividend conquer approach can be written using a line count approach. Initially, the binary search this algorithm is called with input size n. So we can take the time taken for this entire function is t of n. So and then first if condition, so this if condition it's a single statement. So for completing this entire if condition, we can take it as a constant time or single unit time 1. Okay, so just we take it's a constant time. So this is for entire this if statement. So next, this calculating mid value that takes one single unit time, or we can take it as a constant time. And for this if condition also it takes constant time. And then inside this if else statement we call the same binary search function recursively. So the binary search function, as of now we don't know what is the total time taken to complete this. We only know if the input size is n, we take it as the total time as t of n. So now inside the same algorithm I call the same algorithm recursively, but now the input size is reduced. So in the best case, assume that the input size is reduced by half. So now we can take it as t of n by 2. So and for this recursive function call also we can take it as t of n by 2. So the total time t of n is the time taken to complete all the statements written inside that function. That means c plus c plus. So here we have 2 t n by 2 time, but in every time either any one of these two statements will be called. So if this condition is true, this statement will be called. If this condition is false, then this statement will be called. So condition true, this statement will be called if the condition is true. So condition is false, this statement will be called. So any one of these two t of n by 2 will be called. So we cannot add both the time t of n by 2 plus t of n by 2. So because in each time any one of these two recursive function call will be called, so we need to take it as t of n by 2. So in total we can write that t of n equal to t of n by 2. So each time any one of this recursive function call will be called, plus all other constant times can be taken as a single constant time. So this c and this c we can take it as a single constant time. So t of n equal to t of n by 2 plus c. So if you solve this by using substitution method, we can solve it with log n time. So the time complexity of this binary search is log n. So here also we can derive best case and then average case. Here we cannot say it as a worst case, average case, because average case and worst case both are same for this binary search. So best case occur when the element found at the middle position, the key is found matched with the middle element. So in this example, uh, if the key to be searched is 11, so in the first if condition itself, so in the first time itself, the mid value is matched with the key value. When the first time this function is called, this mid value will be matched with the key value. So we have to do only one comparison. So if the key is present at the mid value, then we need to do only one comparison, only one if condition statements will be executed. So the time complexity is O of 1. So average case is this O of log n. Okay, thank you.